All right, you crazy kids, here's your lecture on chemical names and formulas. So in front of you, hopefully you see two formulas, CCl4 and MgCl2. And my question would be, what are their names? And believe it or not, the first thing you have to do when you're naming anything is identify bond type. Depending upon the bond type, we must follow different rules when naming molecules or formula units. So it's like hockey and soccer. In hockey, you have icing. In soccer, you have... Well, you don't have icing. I can't think of anything right now. You have throw-ins, right? So they are different games. They are different rules. So whether or not it's covalent or ionic, they follow different sets of rules. For example, because this is covalent, this is called carbon tetra chloride. And on this other side, I have a metal and a non-metal. This is ionic. This is magnesium chloride. You might notice a major difference that this tetra is in here for carbon tetrachloride. That tetra stands for 4. That lets us know how many chlorines I actually have. On the other side, I don't have what's called a prefix in front of chlorine or chloride because it's an ion. The reason is, when it's ionic, I have predicted charges. Magnesium is 2+, chlorine is 1-. I know I'm going to end up with MgCl2. But on this other side, these are nonmetals. I don't have predicted charges, so you have to use prefixes to indicate how many of each element you have. Major difference. I'm going to go through all these differences with you one by one. We're going to start with ionic, work our way towards covalent. So, naming ionic compounds. We have cations and we have anions for monatomic ions. That means only one atom, not a polyatomic. For cations, the name stays the same. And what I mean by that is if I have a cation of magnesium, 2+, versus just magnesium, not a cation, they're both called magnesium. There's no difference in their actual name. That might seem confusing, but actually it works out in the long run for us. Anions, the name changes. Specifically, the ending changes to IDE. So up top here, you might notice, here we have chlorine, but it changed to chloride. There are only so many nonmetals. I've listed them out here for you so you can see their name and how they change. So nitrogen is nitride, oxide, fluoride, chloride, bromide, iodide, phosphide, sulfide. Those are the only ones you have to worry about. So those are all of your nonmetals, and nonmetals would be anions, and you can see how their name changes to IDE. Then all you got to do is combine the names of the positive and negative anions and cations. For example, this is going to be aluminum oxide. Aluminum, Al3+, in this case, its name does not change. And oxygen, whoa, screen moved, O2-, its name changes to IDE. From aluminum oxide, you should be able to also then form a formula unit. We've already done this before, but aluminum has a predicted charge. Oxygen has a predicted charge. Because of that, I can figure out it's going to be Al2O3. So you should be able to work forwards and backwards, or from a formula to a name, and a name to a formula. I could give you either one and expect you to know what I'm talking about. Our next one down is something very similar, or actually not similar, but familiar to, I guess we could say. This is sodium chloride. Notice how chlorine changes to IDE and sodium keeps its whole name. That'd be Na+ and Cl-. Predicted charges, I still can get NaCl from that name. And then we have CaCl2, that's going to be calcium chloride. Calcium, Ca2+, chlorine, Cl-. I can still get the same formula unit only from the name, CaCl2. Notice how it doesn't matter how many of each atom is present in the name. I never mentioned these subscripts when I named them. That's because they have predicted charges, and because it has a predicted charge, I can figure out those subscripts based upon canceling out those overall charges to have a neutral formula unit or a neutral compound. Next, something a little bit trickier. Naming ionic compounds with transition elements. It says here I must indicate the charge of the metal. I use the stock system of naming. What I mean by that is I have iron and copper here. Iron and copper don't have a predictable charge. Their charge can actually change. Iron can be 2+ or 3+. Copper can be 1+ or 2+. So how do I figure out its charge, and how do I indicate that charge, of the metal? Well, I figure out what it's bonded with, and what it's bonded with usually has a predicted charge. In this first case, I know that oxygen's predicted charge is going to be 2 negative, so that means this iron is going to be 2 positive. When I name it, I'm going to talk about that charge in the actual name. I'm going to use a Roman numeral to indicate its charge. So this is going to be iron 2 oxide. Notice the 2 matches the charge for the iron. In this case, it also matches the charge for the oxygen. That's just a coincidence. Don't lay too heavily upon that. Our next one, CuCl2. I know that chlorine's predicted charge is -1. There happens to be 2 of them. That's a total of 2 negative. That means this copper has to be 2 positive. I would name this copper 2 chloride. The Roman numerals you're going to be responsible for in terms of charge are going to be 1, 2, 3, and 4. If you don't know those, that's 1, 2, 3, and 4 for Roman numerals. You could have a very large charge, but I'm only going to give you up to 4, I think. Tungsten forms like a +7 charge, but I don't think I'm going to give you anything past 4. And if I do, I'm sorry. We'll deal with it later. Now, polyatomic ions. So for ionic compounds, instead of being monatomic, I could have polyatomic, meaning things that have multiple atoms bonded together that also have a charge. It says here, become very familiar with them in your packet. I have said this so many times, it's almost worth memorizing them. We're going to use them all year long. There's not too many to memorize. It's kind of what I would do. This thing right here, I know it because I've seen it so many times. That's called nitride. Nope, nitrate. Nope, nitrite. Wow, I can talk so good right now. All right, so that's nitrite. There's also something called nitrate and something called nitride, which is why I said all 3. Just because I've said them all, let's look at them all real quick. There's nitrite, nitrate, and nitride. Nitrite is NO2 negative, nitrate is NO3 negative, and nitride, IDE, is not a polyatomic ion, it is just N3 negative. So depending upon the spelling, it's going to be kind of important to realize that these are totally different things. And I will be counting spelling on these tests. You have to spell it correctly, otherwise you're naming it improperly. You have a packet in front of you, all the spelling is provided for you, you have all the elements and how they're spelled, so please, please, please spell them appropriately. All right, that was a little sidetrack, but a good one. Let's look at the next one. We have CO3 2 negative, that's called carbonate. Notice how it's ATE, ITE, ATE, IDE. Ooh, this one kind of looks like a monatomic, but hydroxide is not one of those nonmetals I mentioned before. The endings will kind of give you a clue of whether or not it's a polyatomic or a monatomic ion. Usually if it's IDE, that's got to be a monatomic. Hydroxide is kind of an exception to that, and it's OH negative. The key here is hydrogen forms an anion, but most likely it's a cation. Anyway, hydroxide is a polyatomic ion. Just become familiar with it. It's OH negative. Phosphate, PO4, 3 negative. These things you just have to become very familiar with. I can throw a polyatomic with a monatomic, and I just put those 2 names together when I'm naming stuff. For example, down here, I have copper 1 acetate. That means this copper is going to have a +1 charge, and acetate, because I'm familiar with it, is going to be C2H3O2. 3, -1 charge. Therefore, my positives equal my negatives. I don't have to change any numbers of things I have here. So this is going to be Cu, C2, H3O2 as the formula of copper 1 acetate. I put there a transition element with a polyatomic. I can do anything like that, all right? These are all positive and negative things. All I have to do is smash them together, make sure my charges cancel out. My next one, I have NH3, NH4, parentheses 3N. Ooh, all right. This NH4 thing, that's called ammonium. I don't need to mention how many I have, because how many I have is due to the charge of nitrogen in this case, which is 3 negative. Nitrogen is going to change to nitride. And then we have ammonium nitride. If I was working in reverse, I would look at the charges of these things and make sure they add up. For instance, ammonium is going to be NH4 positive, and nitride is going to be N3 negative. Therefore, I would need 3 ammoniums for every nitride ion. All right, that's naming ionic stuff. Now let's jump into naming binary molecular compounds. Binary molecular compounds, we don't have to worry about charges, but we do have to worry about our subscripts, or how many of each element we actually have. To deal with that, we use these things called prefixes, and here they are off on the right-hand side. We'll use a different color. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm very good at counting. So we're going to use prefixes to indicate how many of each element we have, but we also have to follow rules on when to use a prefix. We're only going to be dealing with binary molecular compounds, and an example of a binary molecular compound that you're familiar with is CO2. So only 2 elements present. More than that exist, but I'm not going to deal with naming with those in your first year in chemistry. So if it's a binary molecular compound, that means we're going to have a first element, the first element, and a second element, the second element. The first element's going to rule by these rules. Your second element's going to rule by those rules. We'll go through them to make sure it makes sense. We're going to use CO2, or carbon dioxide, as our example. So the first element looks like you only get a prefix if there's more than one element present. Notice how I didn't say monocarbon, because that sounds ridiculous. I just said carbon when I'm naming carbon dioxide. That's because I didn't have more than one element present. There's no subscript for carbon, so it's just carbon. Simply by saying the word carbon, everybody knows you have one. If I had more than one, I would have to use a prefix to indicate how many I actually had. The second element, you always use a prefix. You always then add the root name, and you add IDE to that element's name. These are all going to be nonmetals. We could scroll up here and see all of your possibilities for your nonmetals. That's how they end in IDE. That's what I mean by root name. The prefixes would go obviously before those names. Let's check it out. So I named this dioxide. That's because it's oxygen. There are 2 of them, and I ended in IDE. So that's prefix, root name, IDE. That's kind of the name of the game, guys. Let's take a look at a couple examples, and then also bring up this weird English language rule in a second. So P4O10. Using my rules, this is going to be tetra, phosphorus. All right, I used a prefix because I had more than one, and then I added the full name of the element. And then I have 10 oxygens. I could name this decaoxide, but that kind of is a mouthful. And because it's a mouthful, they came up with this rule up top here. When you have an O or an A at the end of the prefix, it's dropped if the element starts with a vowel. So instead of decaoxide, I remove that A, and this turns into just decoxide, which, believe it or not, sounds a lot better. Another example of that would be CO, or carbon monoxide. I didn't say monooxide because that sounds ridiculous. I dropped the O from the prefix, and that turned into just monoxide, carbon monoxide. Our last example is Ni3, so I don't need a prefix on my nitrogen. I'm just going to use the full word. And now I have to have 3 iodines, so that's tri, and then iodine is iodide, so I'll say tri-iodide. That one kind of sounds weird, but that's what it is. This is actually some fun stuff. It's pretty explosive when it's dry, but it's stable when it's wet. I used to make it in the classroom until I got a little bit of trouble, and now I don't make it anymore. So anyway, cool stuff. All right, see you later.